So, today we will see the discretization of linearized virtual work expression. Till last lecture we completed the discretization of the equilibrium equations. Okay. So, today we are going to see the discretization of the linearized equilibrium equations. Okay. We have discretized the equilibrium equations, okay, and we had obtained a set of discretized nonlinear equilibrium equation as a function of current nodal positions, okay, x k given by equation 61. Okay. Now, what we have to do is we have to discretize the linearized virtual work expression. Okay. So, you may recall that the spatial virtual work expression is given by the difference of the internal virtual work minus the external virtual work. Okay. And the Eulerian linearized virtual work expression was obtained by taking an increment u in current position psi, and we obtain it as the difference of the linearized virtual work expression, okay, internal virtual work expression, and the linearized external virtual work expression. Okay. So, this term over here is the linearized Eulerian linearized spatial internal virtual work, and this term is the Eulerian linearized spatial external virtual work. Now, as I mentioned in the previous lectures that in this course we will treat that the external forces are independent of the configuration, which means that this particular term is 0. So, we only have to deal with discretization of the Eulerian linearized spatial internal virtual work. Okay. Now, the Eulerian linearized spatial internal virtual work composed of two parts. Okay. So, it is composed of two parts, this is the first part and this is the second part. Okay. So, the first part is because of the constitutive relations, okay, because you see there is a spatial elasticity tensor out here, and the another part, the second part is because of the stress, you see there is a stress. Okay. So, we can write the linearized spatial internal virtual work expression as the sum of the linearized internal virtual work expression because of the constitutive relation and one because of the stresses. Okay. So, these are the expression for the two parts. Okay. Now, we have to discretize each of these parts, okay, this one and this one, that is equation 75 and 76 separately. Okay. So, we will first consider equation number 75, that is we are going to discretize the internal virtual work because of the constitutive relation. Okay. So, the Eulerian linearized internal virtual work expression corresponding to constitutive relation is given by equation number 75. So, I have reproduced it here. Now, this equation 75, when it is written for an element E which links two nodes P and Q. Okay. So, this can be written as summation over nodes P and Q and element E of the linearized internal virtual work expression for belonging to the constitutive relation for element E connecting nodes P and Q by equation number 77. Okay. So, now if I can discretize this expression over here, then I can just take the summation. Okay. Actually, the summation actually implies assembly operator. It is not merely a summation, it is the summation and assembly. Okay. So, I can do the assembly or summation over all the elements over all nodes Q or all nodes P to get the final discretize internal virtual work expression corresponding to the constitutive relation. Notice that NPE here denotes the number of elements which connect to node P, and NPQ denotes the number of nodes Q connected to node P, and NP denotes the total number of nodes in the finite element mesh. Okay. So, now this expression over here can be written as integral over the current volume, the virtual rate of deformation tensor of node P double contracted with the spatial elasticity tensor C double contracted with the strain corresponding to node Q. Okay. So, this is just equation number 75 written for node P and Q and integrated over element E. Okay. So, this is the virtual rate of deformation tensor at node Q, and this is the strain at node Q. Okay. Now, from equations 22 and 24, we know that the discretized strain and the virtual rate of deformation tensors are given by following expression. Okay. So, this we had derived in our previous lecture, and now I can identify this term over here with the strain corresponding to node P. Okay. And I can identify this term as the virtual rate of deformation tensor corresponding to node P. Okay. So, now I can substitute equation 22 and 24. Okay. I can substitute equation 22 and 24 in equation number 78. Okay. So, that is what we have done here. This is nothing but the del epsilon P del d P, and this is nothing but this complete expression is epsilon Q. Okay. I can replace this P by Q here. Okay. It is just the matter of convention, and you will see this is epsilon Q. Okay. And now, for further simplification, I can write equation 79, which is here. Okay. That is in direct notation. I can write this in indicial notation like this. Okay. So, it will be del Vi of node P into gradient of shape function of node P corresponding with xj, and the gradient of shape function corresponding to node P with xi del Vj Cij KL 1 by 2, and this is the strain. Okay. Now, I now can use the major and minor symmetry. So, during hyperelasticity discussion, we had shown that the spatial elasticity tensor C has the major and minor symmetries as it is shown in equation 81 here. Okay. So, if I use these major and minor symmetries one by one, okay, I can reduce equation 80, okay, to following expression. Okay. So, I just have to use equation 81. I can replace, first of all I can use this symmetry over here, then I can use this symmetry, and finally, I can use the other two symmetry, and I can show that equation 80 reduces to following expression. Okay. So, now I can convert this back to direct notation, and I can write this term over here as the virtual velocity vector corresponding to node P, this as the increment u corresponding to node Q, and this term inside this bracket can be identified as a matrix K, which we call as the tangent matrix corresponding to the constitutive relation. Okay. And the explicit relation for this tangent matrix K corresponding to the constitutive relations of element T for nodes P and Q is nothing but integral over the current volume, okay, of del n p by del x j C I j k l del n q by del x l. Okay. Now, to get more consistent, okay, I can just interchange k and j, I can get the tangent matrix corresponding to the constitutive relation. Okay. So, using this expression, once I know my shape functions, okay, I can find out this matrix. Okay. And this matrix will be of size 3 by 3. Okay. Now, in traditional finite element literature, we have a alternate expression for equation 83, okay, and that we can derive in matrix form. Okay. And we will see how that relation compares with our relation number 84, okay, relation given by equation 84. Okay. So, let us start. First, we use the Voigt notation and we can express the Cauchy stress tensor, rate of deformation tensor, okay, and the strain tensor in array form as this. Okay. So, remember the strain tensor is written as epsilon 1 epsilon 2 epsilon 3, okay, that is the normal component, and then you have 2 epsilon 2 epsilon 2 epsilon 3. Remember, this 2 is present over here because there are 2 values of strain. Strain has actually 9 components and we are writing this as 6 cross 1 component, and because epsilon 2 is same as epsilon 1, therefore, I put a 2 here to take into account both the strain values. Okay. And now, the virtual rate of deformation tensor I can write similarly as this vector over here. So, once I have defined my vectors, okay, so this virtual rate of deformation tensor, okay, strain tensor in initial notation we know as following relation. Okay. Now, in initial notation I can write the same as this. Okay. So, you have, so this is a dyad. So, this will be u p I del n p j and this will be del n p I u p j. Okay. So, that is what we have written here. So, more explicitly in terms of the derivative of shape function, I can write the component epsilon I j of the strain tensor as 1 by 2 summation over all the nodes, okay, of the elements u p I del n p by del x j plus del n p by del x I del, okay. So, u p j. Okay. Now, equation 88 I can expand for each value of I and j. Okay. So, I goes from 1 to 3 and j goes from 1 to 3. Okay. So, if I do this and I remember that the vector of vector of displacement is given by this 3 cross 1 vector. So, epsilon 1 I can write as 1 by 2 u 1 p del n p by del x 1 plus del n p by del x 1 u 1 p. So, these two terms are same. So, it becomes twice of u 1 p del n p by del x 1 and this 2 cancels out with the other 2 and we get u 1 p del n p by del x 1 summation over all the nodes of the element E. Okay. So, that is your epsilon 1. Similarly, you can show epsilon 2 as summation over all the nodes of the elements u 2 p del n p by del x 2. Epsilon 3 is summation over all the nodes of the element u 3 p del n p by del x 3. Okay. And this twice of epsilon 1 is nothing but u 1 p del n p by del x 2 plus del n p by del x 1 u 2 p, and similarly we have the other 2 components. Okay. So, this equation number 89. Okay. So, on the left hand side I have the strains and using Voigt notation, if I write them as a vector on the right hand side, I can write as a product of a matrix times a vector UP. Okay. So, that is what we are going to do. So, the strain expressed using Voigt notation, which is shown over here, is nothing but summation over all the nodes of the element, this matrix of the derivative of shape functions with respect to current position times the nodal displacements of node P. Okay. If I write this matrix as BP, okay, then I can write my strain in terms of the gradient of the shape function times the displacement of the nodes. Okay. So, epsilon is nothing but summation over all the nodes of the element of the strain gradient matrix BP times the nodal displacements UP. Okay. Now, this internal virtual work expression corresponding to constitutive relation, okay, we again recall it is written like this. So, for an element E, it is nothing but this integrand integrated over the volume of the element E. Okay. So, using Voigt notation, I can express this relation over here as del D transpose a matrix D into vector of strain epsilon integrated over the current volume of the element E, and we will see what this matrix D is all about. Okay. So, now from equation number 90 and 67, okay, so equation 67 we had derived that the vector of the virtual rate of deformation tensor is nothing but summation over the nodes of element of BP del Vp. Okay. And this BP del Vp I can write it as the vector of virtual rate of deformation tensor corresponding to node P. And similarly, the strain I can write, okay, from equation 90 as BQ UQ and integrated and summed over all the nodes of the element, and this BP UQ I can write as vector epsilon corresponding to node Q. Okay. Now, if I use these here, okay, so I can write P and Q as integral of this integrand over the current volume of the element E. Okay. And now, del D P transpose from equation number 67 is nothing but BP del Vp transpose. So, that is what we have substituted here, and epsilon Q is nothing but BQ UQ. Okay. So, we write BQ UQ. Now, this I can open up, and this is nothing but del Vp transpose BP transpose D BQ UQ, okay, integrated over the current volume of the element. Okay. Now, virtual velocities are independent of the configuration. So, I can take them outside and it becomes del Vp transpose integral of the remaining part is a vector. So, I can replace del Vp transpose by del Vp dot, and then I can take the nodal displacement out from the right hand side here, and I am left with the expression in the bracket, and this is nothing but our tangent matrix corresponding to the constitutive relation, okay, of element E connecting nodes P and Q. Okay. And this tangent matrix is given by equation number 94. Okay. Now, you note that the previous expression and the current expression, there is a little difference. Okay. The difference is this P matrix over here, okay, as you could see here. So, B matrix over here contains a lot of zeros. Okay. So, you see there are a lot of zeros present here. So, when you use equation 94 to compute the tangent matrix, okay, then you will do a lot of zero multiplication. Okay. And this we note that because of the presence of zeros in this strain gradient matrix P, equation 94 is computationally very expensive. Okay. Now, we come to the form for the spatial constitutive matrix D. Okay. And this spatial constitutive matrix D can be obtained from the components of the spatial elasticity tensor C as given by equation number 95. Okay. Where in the present course we are considering a compressible Neo-Hookean material, and the material that we discussed previously, for that particular material this D matrix is given by following form. Okay. Notice that we have zeros and zeros over here, and these correspond to the shear part, okay, and these correspond to the tensile part. Okay. Now, this lambda dash and u dash were given by following expression, and we also noted that for very small deformation determinant of f was nearly equal to 1, that is j was nearly equal to 1. Therefore, mu dash was nearly equal to mu and lambda dash was nearly equal to lambda. In that case, if mu dash is nearly equal to mu and lambda dash is nearly equal to lambda, then this D matrix is nothing but your fourth order elasticity tensor that is discussed in the course of linear elasticity. Okay. The Eulerian linearized internal virtual work expression corresponding to the stress written for an element E having node P connected to node Q is given by following relation. Okay. So, this is that Eulerian linearized internal virtual work expression corresponding to the stresses, and this is nothing but the summation of the linearized internal virtual work corresponding to the stresses for an element E connecting nodes P and Q. Okay. So, here as usual NPE is the number of elements connected to node P, NPQ is the number of nodes Q connected to node P. Okay. And then this term, okay, can be written as the integral over the current volume of sigma double contracted with the gradient of u transpose corresponding to node Q and the gradient of virtual velocities of node P. Okay. Now, I can recognize, okay, I can recognize that the virtual velocities and the displacement were discretized by equation 8 and equation 10. Now, if I take gradient on both the sides, okay, if I take gradient on both the sides as shown here, I will get my expression for the discretized gradient of the virtual velocities, okay, which is here, and the gradient of the displacement which is here. Okay. And now, these terms in the bracket correspond to the gradient of the virtual velocities corresponding to node P, and this is the gradient of displacement corresponding to node Q. Okay. Now, I can substitute equation 98 and 99, I can substitute them in equation number 97b, and once I do this, okay, so this is equation 97b. Now, gradient of u corresponding to node Q is uq tensor product gradient of nq transpose, and this term is variation of virtual velocities. Okay. So, the virtual velocities of node P tensor product gradient of shape functions N P. Okay. And now, this is A tensor product B and C tensor product D. Okay. So, this is nothing but A dot C B tensor product D. Okay. So, A is UQ, B is the virtual velocities corresponding to node P, our B is the gradient of shape functions NQ, and D is nothing but gradient of shape function NP. Okay. And now, notice that this is a scalar, this is a second order tensor. Okay. So, this is a scalar, I can take it outside the bracket, and now I have sigma double contracted with A tensor product B. Okay. So, this is a first order, this is a vector, this is also a vector. Okay. So, sigma double contracted with B will be your B dot sigma A. Okay. So, this is what we have written here, and remember sigma is second order tensor, the gradient of shape function NQ is a vector. So, therefore, this is a vector, and therefore, this vector dotted with this vector gives you a scalar. So, you have a scalar. So, you have to integrate a scalar over the current volume, and then I can write, and because this is a scalar, this is a scalar quantity, I can bring this here, okay, in between this dot product, in dot symbol and displacement of node Q, and I can write this as a tangent matrix, okay, corresponding to the stresses. Okay. And the explicit expression for this tangent matrix corresponding to the stress is identified as integral over the current volume, the scalar quantity times the second order identity tensor I. Okay. So, this is a second order identity tensor that we have to have. Okay. You can obtain the tangent matrix corresponding to the stress using equation 101. Okay. So, in initial notation I can express my equation 1, equation 101 as following relation. Okay. So, remember this delta I j is nothing but this second order tensor. Okay. So, this gradient of NP is nothing but del NP by del xj, sigma is sigma KL, and del NQ is del NQ by del XL. Okay. Remember this is a scalar, this whole term is a scalar. So, we should have all the repeated index. So, K is repeated twice, L is repeated twice. Okay. With this in hand, okay, now the total linearized internal virtual work is the sum of the linear virtual work corresponding to the constitutive relation plus the discretized linear virtual work corresponding to the stresses. Okay. Now, equation 72, okay, we can write, okay. So, the discretized linearized internal virtual work can be written as the discretized internal virtual work corresponding to element E connecting nodes P and Q as equation 103. Okay. And we know that this is nothing but d del W internal corresponding to constitutive relation plus d del W in corresponding to the stresses of E. Okay. So, this is the, okay. So, this is here and this is here. Okay. So, the discretized linearized internal virtual work expression corresponding to constitutive relation is given by equation 77, and the discretized linearized internal virtual work expression corresponding to the stresses even is given by equation number 93. 7a. Okay. Now, I can write the term on the right hand side, that is the right hand side of equation 103. Okay. So, this I can write as the dot product of the virtual velocities corresponding to node P with the tangent matrix corresponding to element E connecting nodes P and Q with displacement of node Q. Okay. So, I know that this is nothing but del V P dot K con P Q U Q, okay, and this is nothing but del V P dot K stress P Q U Q, and this I have written as del V P dot K P Q U Q, okay, corresponding to element E. So, I can write the elemental tangent matrix for node P belonging to element E and connected to node Q as the sum of the constitutive tangent matrix and the stress tangent matrix, okay, with the explicit expression for the constitutive tangent matrix is given by equation 84 and the explicit relation for the tangent matrix corresponding to the stress is given by equation 101. Okay. So, once the elemental tangent matrix, which is this over here, this if we have found out corresponding to nodes P and Q, then the global tangent matrix required for the Newton-Raphson scheme can be find out as follows. Okay. In step 1, the contribution to node P from node Q from all the elements which contain nodes P and Q respectively is assembled. Okay. So, you first assemble all the contribution to node P from node Q, okay, from the elements which contains both nodes P and node Q. So, in a finite element mesh, for example, you may have something like this, and this is say node P and this is say node Q. So, we have to first assemble the virtual work, internal virtual work from the discretized internal virtual work from all the elements which contain both node P and Q. So, for example, this element over here and this element over here, these two elements contain both nodes P and Q. So, we obtain the tangent matrix from these two elements and assemble to get the contribution to node P. Okay. And then next what we do, the contribution to node Q from all nodes Q which are connected to node P, this is assembled. Okay. So, in a finite element setting, this is your node P, then corresponding to node P you have Q1, Q2, Q3 and Q4. Okay. So, 4 nodes are connected. So, you take this contribution for each node which is connected to node P and then you assemble. Okay. So, this remember this summation sign means actually addition and assembly both. Okay. So, once you have got the internal virtual work corresponding to the node P, in a similar fashion you do for all the other nodes in the finite element mesh. So, contribution for all the other nodes of the finite element mesh are then assembled to get the final discretized internal virtual work, okay, for the mesh. Okay. And this final assembly will result in the following expression. So, this discretized version of the linearized internal virtual work, okay, over the mesh is nothing but velocity vector with the dot product with the global displacement vector, okay, where the final global virtual velocity vector is given by this vector over here, where NP denotes the all the nodes present in the finite element mesh, and the global displacement vector, that is the vector of unknown, is the displacement of all the nodes present in the mesh. Okay. And this tangent matrix, okay, and this K, what is called the global tangent matrix. Okay. So, this global tangent matrix is composed of K11, K12. Okay. So, K11 is actually, so remember we had K P Q. So, here P is 1, Q is 1. So, K11 means the contribution to the tangent matrix coming from node 1 interacting with itself. K12 means the contribution to the tangent matrix coming to node 1 because of a small change in node 2. Okay. Like this, you will get the final global assembled matrix. And remember, each of these matrix is of size 3 cross 3. Okay. So, considering 3 degrees of freedom per node, the total size will be 3 NP cross 3 NP. And remember, a lot of these tangent matrices components may be equal to 0. Okay. So, for example, this may be a 0 by 0 0 0 matrix. Okay. So, from your connectivity matrix, you can actually find out which of these components will be a 0 matrix. Okay. So, once we have obtained our global tangent matrix, I can now move to setting up my Newton-Raphson iteration. Okay. So, next we will do one small example to understand what we have discussed today, and we will do it for a simple 2D triangular element, and we will derive most of these expressions, so that you understand what we have discussed today. Okay. So, next we do one example to understand the mathematical details that we discussed in previous slides. Okay. So, in this example, you have a triangular finite element, okay, as shown in this figure. Okay. So, this triangular finite element deforms, okay, and it occupies this position, say at time t. Okay. So, this say maybe this is at time 0. Okay. And now, the nodal position of node A, B and C are given here before the deformation, and after the deformation, the nodal positions A, B, C of node 1, 2 and 3. Okay. So, node 1, 2 and 3 are shown here, and then we have to find the matrix of the gradient of shape function with respect to the natural coordinates psi 1 and psi 2. So, the direction of psi 1 and psi 2 are shown here, and then we have to find the derivative of the material coordinates with respect to the natural coordinates, and the derivative of the spatial coordinates with respect to natural coordinates. Then we have been asked to find out the derivative of the shape functions of the node with respect to material coordinates, and also the derivative of the shape function of the nodes with respect to the spatial coordinates. Okay. And finally, we have been asked to find out the deformation gradient tensor f. Okay. So, let us see how we can proceed. Okay. So, we have been given the material coordinates. So, let us say this is our x 1, this is 0 0, x 2 which is 2 0. So, this is node A, this is node B and this is node C, okay, and this is 0 1.5. Okay. And now, the spatial coordinates of the same nodes A, B and C after the deformation are given to be 3 4, 7 4 and 7 8. So, what we have done here, we have expressed the coordinates in array form. Okay. So, you see we have express the coordinates in array form, and this is essential for finite element implementation. So, that we can do these operations on a computer. Okay. Because this is a simple example, we can do it by hand, but in actual situation we have to do it on a computer, because there will be many such finite elements. Okay. So, the shape functions of the 3 nodes. So, there are total 3 nodes, and n 1 is 1 minus xi 1 xi 2, n 2 is xi 1 and n 3 is xi 2. Okay. So, we can calculate the derivative of the shape function as del n 1 by del psi, okay, which is nothing but del n 1 by del psi 1 and del n 1 by del psi 2. Okay. So, if you look here, del n 1 by del psi 1, okay. So, there are only minus psi 1. So, we get minus 1, del n 1 by del psi 2, there is minus psi 2. So, we get minus 1. Okay. Similarly, del n 2 by del psi in array form is del n 2 by del psi 1, del n 2 by del psi 2, and n 2 is independent of psi 2, therefore, we have 0, and n 2 is directly equal to psi 1. So, we get 1. Okay. Similarly, we can compute del n 3 by del psi, and in the array form this is 0 1. Okay. Once we have calculated the derivative of the shape function with respect to the natural coordinates, we next see that the material and spatial coordinates of a point inside the element. So, you have a triangular finite element and you want to get its material and spatial position with respect to its nodal, say x 1, x 1, x 2, okay, x 2, x 3, x 3. Okay. So, you can get the position, okay, current coordinates and the reference coordinate of any point inside the element in terms of its nodal values. Okay. With this in hand, okay, I can substitute n 1, n 2, n 3 and the coordinates x 1, x 2, x 3 in the expression, okay, and I can get the coordinate of any point inside the finite element in terms of psi 1 and psi 2. Okay. Similarly, I can do it for the current spatial position, okay, and I can get the current spatial position inside the same point in terms of the natural coordinates like this. Okay. So, these are the coordinates of the nodes, okay. These are the coordinates of the nodes, and these are the shape functions n 1, n 2, n 3. Okay. So, I get the current spatial position of the point in terms of the natural coordinates psi 1, psi 2, psi 3. Now, I can compute the derivative of the material and spatial coordinate of a point inside the element with respect to the natural coordinates using the following formula. So, del x by del psi is given by this matrix, and I already know that x 1 is 2 psi 1 and x 2 is 1.5 psi 2. So, I can get the matrix del x by del psi as 2 0 0 1.5. A similar procedure when applied for the derivative of the spatial coordinate with respect to the natural coordinates, I get 4 4 0 4. Okay. So, now once I have del x by del psi and del x by del psi, I can compute the inverse transpose. Remember, we need this. So, I can compute the inverse transpose, and with this formula, okay, the equation number 16, the derivative of the shape function with respect to the material coordinates is nothing but del x by del psi inverse transpose del n p by del psi. And now, I have my del x by del psi inverse transpose like this. So, that I can substitute, and del n p by del psi I have it from the previous slides. Okay. So, for p equal to 1, I can substitute and I can get the expression del n1 by del x as minus 0.5 minus 2 by 3. For p equal to 2, okay. So, this is p equal to 2, I can substitute, okay, del n2 by del psi, which is 1 0, and I get the del n2 by del x. So, derivative of the second shape function with respect to material coordinates at 0.50, and for the third node I can compute the third derivative, I mean the derivative of the third shape function with respect to material coordinate as 0, 2 by 3. Okay. Once we have done this, I can follow a similar procedure and I can get the derivative of the first shape function with respect to the spatial coordinates as 0.250, the derivative of the second shape function with respect to spatial coordinates as 0.25 minus 0.25, the derivative of the third shape function with respect to spatial coordinates as 0.25. Once we have this in position, okay, I can now, using equation number 14, I can compute my deformation gradient tensor using the formula given here. Okay. So, if I now see my n, the total number of nodes in the element are 3. Okay. My small j varies from 1 to 2 because it is a 2 dimensional problem, and capital J varies from 1 to 2. Now, if I expand this term explicitly in terms of p. So, I remove this summation sign and I get following expression. Now, using different values of j and j, I can compute the different components of the deformation gradient tensor. Okay. So, let us say if I put small j as 1 and capital J as 1, this is my expression. Okay. So, what this means is x 1 1 del n 1 by del x 1, okay, that is we have here. Then we will have x 1 2 del n 2 by del x 1, that we have here, and we have x 1 3 del n 3 by del x j. Okay. So, this x 1 1 means is the x 1 coordinate of node 1, this is the x 1 coordinate of node 2, this is the x 1 coordinate of node 3. Okay. And we have already calculated the derivative of the shape functions with respect to the material coordinates from the previous slide, and when we substitute, okay, and when we do all these operations, we get the deformation gradient tensor, okay, as 2.667 0 0 2.667 0 0 0 1. Remember, I have added the last row and the last column because for the sake of completeness. Okay. Otherwise, our answer will be this 2 by 2 matrix. Okay. We can also think x 3 was capital X 3. So, f 3 3 was nothing but del x 3 by del x 3, which is nothing but because there is no deformation in the third direction. Therefore, the deformation gradient tensor will come out to be 1. Okay. So, with this we come to the end of this particular module on discretization. Okay. Next, we move to our final module, which will be on the solution procedures for solving the equations that we have obtained. Okay. Thank you.